The answer turns out to be none of these, but if you thought ring, that was true for a little while, and if you thought hypercube, that was true pretty much for the same amount of time. And I actually thought the answer was hypercube until I drew out a picture and discovered that it wasn't. So here's why. Again, in the case where n equals 1, it's just a single node. In the case of n equals 2, it's one single node that's half the graph and one single node that's the other half of the graph, and then individual subgraphs have their nodes randomly ordered, but there's just one of them, so there's only one order, and then we connect up the corresponding nodes, but there's just one of them, so it's just that. Okay, in the n equals 4 case, we have n equals 2 graphs, and then the algorithm arbitrarily orders the two nodes in the two subgraphs, but it looks the same either way. If we flip this around, it still looks the same. So let's pretend I flip this one around, and then we connect up the corresponding nodes, and now we get something that is a ring. It's also a hypercube. Actually, all these have been hypercubes so far. All right, let's move up to n equals 8. So in the n equals 8 case, we first generate two n equals 4 graphs, which we know what they look like from before. Then we arbitrarily order these nodes in the two different graphs and connect up the corresponding nodes. So this is where it gets sort of weird. So in a normal hypercube, we would connect this corner, this corner, this corner. So let's start off that way. Because the nodes are randomly ordered, we could actually get something like this, where the top is nice and parallel and the bottom is crossy. This is not a hypercube, but it's sort of hypercube-ish. And as we grow this to larger and larger n, we get tanglier and tanglier structures. And so the nice thing about these structures is they do kind of have an essence of looking like real social network graphs. They have some complexity to them. They're still not quite what we're looking for. But let's do an analysis of this graph, then call it a day. So we can express the number of edges in the tangled hypercube again using a recurrence relation. So now the recurrence relation has this form. For an n-node graph, we generate two n over 2 node graphs, connect up the kind of parallel nodes, and that introduces n new edges. Once again, we can think about this as happening in a kind of recursion tree. We first consider generating a graph with n nodes. We do that by generating two graphs of n over 2. Each of those actually requires two graphs of size n over 4. Each of these levels, we're going to be generating n new edges at this top level, n over 2 for this subgraph, and n over 2 for this subgraph, which adds up to n over 4 for this one, n over 4 for this one, n over 4 for this one, and n over 4 for this one, which adds up to n. And I don't know if you can see what's going to happen here, but we get n edge contributions at each of these levels, and you may recall that there are log n levels to this tree. At the end of the day, the total number of edges that are created is n times the logarithm of n, or n log n. This basic structure comes up a lot in algorithm analysis, which is one of the reasons that I was generating the graph this way. What we're going to get into next time is actually running some algorithms on graphs of various sorts and trying to analyze the algorithms to see how long they actually take to run.